course, our topic for today is linear momentum. And why we are talking linear, because to differentiate between linear and angular. We will discuss angular momentum later. Now here, I'm talking about objects that they are moving in a straight line. And we define inertia in motion to be the linear momentum. Then when you have a mass that is moving, it should have momentum. Okay, we will talk, of course, remember last time we were talking about kinetic energy. Then this object, when it is a mass that is in motion, it has momentum and it has kinetic energy as well. Momentum can be calculated as mass times V. It's a vector quantity, and it has the same direction as velocity. Of course, momentum can have that unit, kilograms, meters per second. It doesn't have a special name. It is just kilograms, meters per second. Any questions so far? Now, momentum and energy are really concepts for systems, not for objects, which means that most of the time, I want to know what is really the momentum of a system. And then I will, let's say here, I have two objects, 1 and 2. They might be both in motion, one in motion, the other one is not in motion. If I wish to calculate the total momentum, it's going to be M1 times V1 plus M2 V2. Okay, now here, like from the previous chapters, we know Newton's second law, net force equals MA. And then I can here substitute instead of A, delta V divided by delta T. And this is V final minus V initial divided by time. I can go through that derivation, and finally, I will find that sigma F, the net force, has to do with the change in momentum over time. Then if there is a change in momentum, okay, then I must apply a force. Like you cannot change momentum without external forces. And hence, when I have no external forces, which means sigma F equals 0, then delta P over delta T is 0, and the total linear momentum will not change. And here we will say total linear momentum is conserved. Here I am talking about external forces, not internal forces. Hello. I'm so sorry, I was disconnected. There was a power outage suddenly. I'm so sorry. All right. There was a sudden outage. I don't know. All right. All right, let me go back to the screen share. You know, I'm sorry that for today, it seems that my the network here, it's not stable. The reason is maybe because of the rain. My panel was like maybe having some difficulties. I don't know. Like, yeah, maybe this, maybe I'm not sure if it is because of the rain. Anyway. Okay, then you can see now my screen. And here I want to differentiate between external forces versus internal forces. Then I consider my two objects as they are really in one system. And then the internal forces, the ones here, they will cancel. Okay, then I'm not talking about the internal, I'm talking about the external. Then when the external forces are really zero, what we are going to get, we are going to get momentum conserved. Okay, what does it mean conserved? If I will add all the momenta before and add all the momenta after, they're gonna be equal. Okay, and here I did show you that this is before collision, mass 1 V1, and mass 2, it has V2. Now that velocity can be to the left, can be to the right. If it is to the left, you should give it a negative. Now after collision, I have V1 prime, okay, and V2 prime. Then I'm using the prime to say after collision. I will not use F. The reason is I will have these like, I will say too many subscripts. Now, when I have external forces like friction, I cannot apply conservation of momentum. Okay, but when the external forces doesn't equal zero, then I will say that is gonna cause a change in the velocity or the change in the momentum. And we define in here a new quantity, we call it impulse, that equals the force times time. Based on this, it has the units of newtons times seconds, which is the same, which is equivalent to kilograms meters per second. Any questions here? Now, in any car accident, and I will assume I have a driver, a good driver, driving 65 miles per hour, he or she will notice there is a hazard on the road, finally will stop. Now, the change in the momentum is constant, the same whether the driver is wearing the seat belt or not, or having the airbags or not. Okay, because I will say the change in momentum depends on the initial and final velocities. But with a seat belt, we're going to see that the time is extended. Then you are making the time of the accident long enough so that your force is going to be small. Versus if you don't have your seat belt, you're going to have the time very short, and hence you are going to have the force is going to be very big, and this is going to make the accident, which like with more severe, let's say, injuries, or maybe, you know, anything that is going to happen. Also here, I am trying to demonstrate this using, if I have a car again moving with 65 miles per hour, there is a hazard on the road, and the driver has an option of hitting a stay, a stack of hay, or a wall of cement. In both cases, again, the car will finally stop. When I'm gonna ask you when delta V is greater in scenario 1 or 2, it's the same in both, because the car was initially at 65 miles per hour and then finally at 0. Now, which delta P, which change in momentum is greatest? Both the same, because the change in momentum depends on the change in the velocity. What about the impulse? Again, the impulse is the same, because the two cases, we have the same change in momentum, and impulse equal change in momentum. And finally, which one is going to be the force greater? And of course, here we are going to get, this is going to take longer time versus this one is going to take a short time. And this is when we have the force is greater at 2 because the time is shorter and we might have severe injuries.
I have a question.
Yes.
Okay, why is the impulse the same if impulse is equal to the force times time?
Yeah,
wouldn't
because
the force be greater in the cement?
All right, excellent. I said, okay, now here, I said impulse 1 equals impulse 2. Now, in the case, let me add a page here. Okay, in the case of the wall of cement, we said the force is going to be great, right? And in the case of the haystack, the force is small. Here, the force at the time is more, and here the time is short. Okay, let me give you numbers. Let's assume you're gonna have 2 seconds in your in the accident hitting the hay of stack versus here 0.2 seconds. Now, in order for these to be equal, if this force is gonna be, let's say 10, let's say assume 10, 10 times 2 is 20. 20 divided by 0.2, that force here is gonna be 20 divided by, multiplied by 2, divided. This is gonna make this 100. Okay, what did I do? I'm sorry, I reversed the times. Okay, here is the short time, here is the long time, which is the 2, let's say, seconds. And then I will assume here I have 0.2 seconds, like this is gonna be the time very short. Then this is 200 divided by 0.2. This is gonna be to 1,000. Okay, then if you look here, look at the times. In order for the car to hit the wall of cement, it will take a very short time, which is 0.2 seconds. And therefore the force is really big or large. Versus is gonna, for the hay of stack, is gonna take a longer time, then the force relatively is smaller. But you can say here, impulse 1 equals impulse 2, right? If you multiply 0.2 times 1,000 is what? 200. And 2 times 100 is 200. Then the impulse is the same in both cases, but in one of the cases, the time is really short, then the force is big, and the other time, the time is long, and this is the reason why the force is less. Does this answer your question?
Yes, thank you.
You're welcome. Now, also, we can calculate the impulse from the area under the curve. And here we are calculating the absolute value of J, which is the impulse. And then I will say, for example, if I have this graph, the maximum here is 13 newtons, right? And I can dissect this into area 1 and area 2. These are two triangles. The first one, the area is going to be 1/2 9 times 13. And the other one is going to be 1/2 times 9 times 13. And then I can say that I will have this amount of impulse based on the calculation from the graph. Okay, then you can simply say it's going to be 9 times. Yeah, here because they are equal, I will say because they are like two triangles that they are really the same, but sometimes you might have another situation, like different shapes. You might have a triangle, you might have a triangle, you might have a rectangle, a square. Whatever you are going to have, you can calculate the area under the curve. And this is going to give you what is really the impulse here. Questions? Now I have one example here just to show you when we're going to work on conservation of momentum. When sigma F equals, or like the external forces acting on the object equals 0. And I have here this object mass 1, it is 0.5 kilograms, and the other one is 0.3 kilograms. The first one is moving to the right in 2 meters per second, and the other one is moving to the left in 2 meters per second. And this is the reason why I'm giving it a negative. And the velocity of this first one was given as 1 meters per second after the collision. And I'm looking for what is the velocity of mass 2 after the collision. Okay, now I can say, of course, Pi equals P final, and then M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. And then I will substitute my values, 0.5 times 2 plus 0.3 times -2, and then equals 0.5 times 1 plus 0.3 times V2 prime. And I will be able to solve for the velocity of the second object as a -0.33 meters per second. Then that object is going to move to the left with 0.33 meters per second. All right. Now, you will hear me always talking during this chapter about collisions. And collisions, I don't mean only the ones on the road. Here in physics, a collision is an event that is going to include interaction between two objects for a very short time. Now, what does that mean? That means that they're gonna, like the two objects, they're gonna come together, they're gonna touch each other, they're gonna be in contact. During that time, we're going to have the force from the first object on the second equals negative the force from the second one on the first one. This means that the forces they're gonna receive during the collision, they are equal in magnitude, but they are opposite in direction. Okay, each interaction is gonna have two forces. Now, the first collision that I'm gonna consider here, it is one type of very important collisions, which is called elastic collisions. And these elastic collisions, okay, and this is, we are going to have here, okay, the elastic collision. Now, the elastic collision is a collision that can occur between marbles, billiard balls. These are really considered to be elastic collisions. Now, momentum is conserved in all types of collision, not only in elastic. Now, there is one type of collisions, we call it head-on. This is the one that I'm going to discuss now, which is when they are going to be their center of mass on the same straight line. This one, we call it head-on collision. Okay. All right. Now, I can apply conservation of momentum, okay, which is mass 1 times V1 plus mass 2 V2 prime equals mass 1 V1 prime plus mass 2 V2 prime. And I can also say that kinetic energy is conserved here in this type of collisions. Then if I have calculated the total amount of kinetic energy before should equal the total kinetic energy after. All right. Now I have derived an equation that is going to make it easier for us to use. This is talking about the final velocity of the second minus the initial velocity of the first equal the minus the difference between the velocities before collision. And this one is much easier to use than the one which is talking about kinetic energy, because remember the kinetic energy one, just 1 second. I need to get my phone. Sorry. All right, then now here, that I advise you to use the second one that I gave you, not the first one. The first one, it is good in some situations. You're gonna find one example in your textbook, but in most of the cases, I like to use the first one, the second one. The second one, it is making it easier because we don't have square in it. Any questions here? Okay. Now, let me show you how I'm gonna solve one elastic collision problem here. I have two objects, the same objects that I did use in the first example, but here I'm gonna assume that my collision is elastic. And I'm gonna solve based on that. All right. Now, let me first apply the first equation, which is conservation of momentum. I did plug in my numbers, and then I have two unknowns here. I don't know what is my V1 prime, and I don't know what is my V2 prime. The velocities after the collision, I don't know these. I can here create an equation, and then I'm gonna use the second equation that I told you, the V2 prime minus V1 prime equals minus V2 minus V1 to form my second equation. Now I have two equations with two unknowns, then I will be able to solve the one, like V2 prime equals V1 prime plus 4. You can substitute this into the equation, and from that you can get what are the velocities after the collision, V1 prime and V2 prime. Okay, this is 8A. I have also here, I did record for you the completely inelastic this morning. This is a very short, I meant to have it like a very short, and I'm gonna post another one for two-dimensional collisions. I will finish this one with you, and the third one, I'm gonna post it recorded because I want you to, pay extra attention to that. It is two-dimensional and it's a little bit maybe not easy to understand, which I recommend review the components before, or like vectors before going through that. Now, here I'm talking about one of the most important collisions, which is completely inelastic collision. Now, how should we know that this is completely inelastic? It is when the two objects, they're gonna stick together and they will move as one unit. There are many car accidents or like collisions where the objects, they're gonna stick together, they're gonna move as one unit. And here I'm giving you one of the examples where I have mass 1 has a mass which is 0.1 moving to the right, and mass 2 with a velocity -1 meters per second because it is moving to the left, and it has 0.4 kilogram mass. They're gonna stick together and they are going to move. And I'm asking you to calculate the velocity of the combined mass after collision. Here, only we can apply conservation of momentum. Kinetic energy is not conserved. It will not, if you calculate before and after, it's not gonna be equal. It's gonna be less after the collision. Then here I will say M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. Now, since the two masses, they have the same velocity, I can combine the masses together and I can get this equation. Then I can plug in my numbers and finally calculate the velocity of the system, the two masses together, to be 0.8 meters per second to the right. Most of the time in these type of questions, I might ask, what is the change in the total kinetic energy of the system? And here I want you to pay attention that it is always the change is gonna be final minus initial, which means in these completely inelastic collisions, we are going to have that number as negative since there is a decrease in the kinetic energy. The first one, I will calculate the total kinetic energy before Ki, which is 1/2 M1 V1 squared plus 1/2 M2 V2 squared. And then I'm gonna calculate the final here, like I can easily say, all right, what I have is 0.5 times 0.1 times 8 times 8, that is gonna be 3.2. And the other one, it is 0.5 times 0.4. And of course, this is 1, then this is minus 0.2. Then Ki is 3 joules. And K final is 0.5 times 0.5 times, okay, 0.5 times 0.5 times 0.8 times 0.8, and that is 0.16 joules. And then when I will subtract 0.1 joules, 0.16 joules minus 3 joules, this is where I'm gonna get the negative. Okay, then here the energy, the kinetic energy was lost during the collision. And we will say sometimes we don't like to say lost, we will say dissipated, which means it is converted into other types that we cannot reuse again. Any questions here?
The video for this will be uploaded later.
It should be, isn't it? Can you check it for me?
Chapter AB
Yeah,
is
is it
this
working?
is the same video as chapter 8A.
Oh, yeah, okay,
Yeah.
this is the problem again, yeah. All right, then I'm gonna post this recording. I mean, yeah, I can post the Zoom recording. And I'm gonna record the third one, but just I need to contact them to see what's wrong. Or I will upload again to YouTube and then I will put it for you, okay? Because I don't know why I have, this is Screen-O-Matic. I'm using it for a while now, but now every time I'm trying to upload a file, it will load the one before, although I was working with the file. Anyway, I'm so sorry for this, but like I will fix it today for sure. Okay, there is another part that I will post today, hopefully, okay? The part C. Any questions? Okay, then also remember this Friday, we are going to have our third exam. It's gonna be the chapter about energy and momentum. No questions? Okay, then I'm gonna end the Zoom now. Okay, thank you. Thank you for being here and your patience with me today. Thank you.